drawings. Now, if you want to bring something in, you're very careful about it, fine, but they go bananas. I mean, especially with stuff like tobacco, people dump over those bottles they fill with. Something like that, it makes a real ugly mess, and it's a problem. So nothing like that, but I will not prevent any kind of, especially coffee or something like that, from coming in. I do ask you to be here every day, but I don't take attendance. Now, the only reason I don't take attendance is because, frankly, it takes too long to do that. I mean, how many of you know who Dr. Gross is? Have you had Dr. Gross? No, you haven't. For what?
For power.
He always suggests to give a 1-minute quiz at the beginning of class where you put your name on a paper. So I don't do that. You want to come, please come. And if you can't come, or you don't want to, you can watch the video, but you're responsible for everything covered in class. So I'm telling you that straight up front. Another thing I'm going to tell you is that probably the most dangerous thing to do is go and work with some of these groups that will do your problems or something like that for you, and what is it called? There's Chegg or something like that. There's all these things. The reason is because usually I'm finding out these people are geared for the masses in physics, and the answers they give you are wrong. So you come take a test and you completely blow it, and it's like, well, they're using CGS units, this is MKS units, you know, don't listen to them. So I'm just making that as a suggestion. Now I will say this, YouTube has a lot of resources on there where lecture material is available. My lectures are available from long ago, but really good lectures from, like MIT has all this stuff that's open source and stuff like that. So if you want to do that, more power to you, but please be careful of some of these places that ask you for your money and they're going to do your assignments. I just have had some bad experiences. Another thing is that everything is, it builds on what's been done. So the stuff we do at the end of the course assumes you understand the stuff at the beginning, or you're never going to understand the end. So this is one of those courses where everything builds on prior material. And if you have gaps, which does happen sometimes when you got project and stuff, you can really hurt yourself unless you make up that time. I'm just warning you about this. I'm trying to encourage you to do the best you can in this course, because it's not a difficult course, but it is something that requires you to at least be very aware of what can happen if you're not very attentive to it. So, how many have this book again? We're going to start the very beginning. This is going to be, I'll just mention a few things in chapter 1. How many have had physics here in this university? Okay, if you've had physics here, most of the stuff is second nature. So I'm going to go over some of the basic concepts that you probably have down, but I want to make sure you understand. So first thing is, when we have a signal, any type of a signal in the time domain, it doesn't matter if it's electromagnetic, you know, these are brand new markers, but this happens to me every year. They're already dried out. We'll use this one. If this is the axis time, and just suppose I have a voltage here, V of t, and I'm going to say V of t is equal to some value, say A times the cosine of omega t, and we'll call it in volts. Can everybody see that okay in the back? If you can't, please move down. Just move on down. All right, that's a standard type of waveform. Here, the omega term is really 2 pi f, where f would be the frequency of the signal in hertz. Are you familiar with that, everybody? How many are? So I can move on quickly. Okay. Now, when you look at this, because it's a cosine waveform, it will have this type of a variation. And it will have a peak height of A, minimum value of minus A, right? Now, the concept of period is the first thing I'm going to talk about. It's similar to wavelength, but the period is the distance over which this repeats itself. The symbol for the period is T. How many are familiar with that? That's very common. In physics and math, you use that all the time, right? And T is what? Well, technically, if you look at this, place here this part. What I'm really doing is finding the distance over which, really distance over which it repeats itself. The next part, it'll repeat itself, another period, and it keeps on repeating itself. So the way you always get this is you look at what you're plotting. I'm plotting omega t. When omega t is 0, I'm right here, right? That would be 0. When omega t is equal to 2 pi, I'm right here, right? So it'd be omega t equals 2 pi, or really, if I look at this, small t, really t here would be 2 pi over omega. You all agree with that? And that's exactly the definition of a period. The period of the waveform. Now, if you take a look at this, since omega is 2 pi, the period you can see is actually equal to simply 1 over the frequency. And that would be considered really the basic frequency for any type of harmonic operation, cosine, sine, or anything. You all familiar with this class? How many are? Have you all had circuits? If you had circuits, this stuff is probably pretty obvious by now. You've had it. Anyway, so this is really the period of the waveform, and that is really how you actually get the period from a cosine waveform. It has to be repetitive. Next, we talk about something called wavelength. Wavelength symbol is that in this book. It's got a lot of different symbols in different books, but we use that symbol for wavelength here. Wavelength is in meters. All right. And now if we do the same thing, but here I'm going to do something a little different. I'm going to say V of t is going to be equal to cosine of omega t as before, but now it's minus beta, and call this distance z. Are you everybody okay with that? That would be in volts, and I'm just trying to be very simple about it. This is the equation for a wave. It's a solution to something called the wave equation, and you'll see that later. But right now, I just want to make sure you understand that that's a basic type of waveform description. It's really a cosinusoidal waveform. Now, if you let t equal 0 here, we're going to make that stipulation, and you plotted this, you would have V of t is equal to just cosine of minus beta z. Do you all agree with that? I'm making sure you see what I'm talking about. Can you all follow me on that? Now, how many know what an even function is, or an odd? How many know? What's the definition of an even function? And I'll put it over here. If a function's even, what? F of t is equal to f of minus t. It basically doesn't matter about the signage in there. If it's plus or minus the same, it'll be the same value. An example of that would be something if you plotted versus time if it did this. All right? Same value on either side at a given distance away from the origin. Do y'all follow me on this? An odd function is f of t is equal to minus f of t. An odd function would look like this. And I'm being very sloppy, but y'all follow me? How many remember something like that? How many know what a cosine function is? Is it even or odd?
Even.
How many know it's even? It's an even function. Put in cosine of what? 30 degrees, it's the same thing as cosine of minus 30 degrees. Do y'all follow me on that? All right, that means I can just do this. Right. Remember, this is still going to be not V of t, but V of z now. And now when I look at V of z, I got rid of time, and I plot it. What I call this is taking a snapshot in time, freezing time and looking at how the waveform will look spatially. Now if I plot that, I get the same exact type of behavior, right? It'll just go on and on, let's see. And the actual distance over which it repeats itself is now called a wavelength, not a period. Y'all follow me? Before, in time, it was what? Period, because we're plotting versus time. We froze distance in a second. Here, we freeze time, and when we plot it, we get this. Well, at this point right here, that's where z is 0, right? All right, now keep going. Here, what is it? Beta z is equal to 2 pi, right? Isn't that right? Or Z is what? Z, which will be the definition of wavelength, is what? It's going to be 2 pi over beta. And that's the definition of wavelength. That's how you get it from plotting it. It only makes sense if you have periodic functions. Now, usually when we talk about wavelength, we're talking about sinusoids, cosinusoids, or some combination. We're not talking about square waves. Wavelength there is a little, it's not exact, and it has a lot of different meanings for different people. But you all follow me on this, guys? How many of you remember seeing this stuff? This is basic. You should have seen it in physics for sure. But this stuff over here, you should have seen in circuits over and over again. Okay, now I got those two things out of the way. Now, I'm trying to follow what her book has. You all know about phasors, I assume, right? If you've had circuits, you know phasors. You know why phasors are important. So here's my next bit of stuff I have to talk about. Hopefully it'll make sense to you. So we're going to be talking about phasors next. And what I'd like to do is make you aware of something that you'll get in an interview occasionally to see if you actually know what you're doing. They'll come up, and if you're interviewing at Intel, and they'll say, this is a problem I want you to solve. And they'll say this is, say, oh, I don't know, 5 cosine of 30t volts here. And they'll put a resistor here, make it 100 ohms. Then they'll put an inductor here. And they'll make L here like 1 Henry. And they're going to ask for the current I of t. They want you to solve it. Follow? Now there's one thing about this problem that's unique. There's no switch in that problem. The assumption is that voltage has been there forever. You all follow me in this class? So how would you solve that problem if I ultimately wanted I of t? Well, you can do it fairly easy. By looking at this, what is the value of omega just by inspection?
30.
It's 30. If you can't read my writing, I'm sorry. I'll try to do that. Y'all follow me? That's in radians per second. Y'all follow me? Now, when I look at this, you know something also. You know the impedance is really going to be what? It's J omega L would be the impedance in ohms, but it would be complex. How many realize that? I hope every one of you do, really, because if you had circuits, this should be second nature, but you're not used to being asked this type of question. When you go for an interview, they'll ask you. So you would naturally say to yourself, what I'm going to do, I'm going to go ahead and say, I'll do this in the phasor domain. And I'll say this voltage can be represented as a phasor as what? 5 at an angle of 0 degrees. Do you all agree with that, class? So I'll put it over here. 5 volts at an angle of 0 degrees. Now the resistance is the same anywhere. It's still going to be 100 ohms, right? Correct? What about the inductance? I replace that with what? J times 30, right, times L, which is 1, or J 30 ohms, correct? Y'all follow me on what I'm trying to show you? It's that simple. Now what's the current, the phasor current going to be flowing through here? Well, how do you always get it? You got 2 elements in series, right? Add up the impedance, right? Add them in series and divide it into the voltage that's the forcing function causing it. So you can say this phasor current would simply be 5 at an angle of 0 degrees divided by 100 plus J30. Correct, class? Now that's a complex number. It has a magnitude and an angle. Does anybody have a calculator here? Anybody have a calculator where they can give me the magnitude and angle there? I can't do this one in my head. I want the magnitude and the phase angle. And give me the angle in degrees. even though it probably should be in radians from what we're about to do next. While they're doing that, I appreciate you doing that. How do I get it back into the time domain? Don't answer that. Just think about it for a second. Because I wanted the time domain. Remember, the guys interviewing you is asking you about the time domain, not frequency domain solution for this. But there is no switch, so there's no transient, thankfully. Did you get it? What'd you get?
0.0479 at an angle of -16. 0.69.
7. How many got that? That would be amps. Do you all agree with that? You got it? Did you get it? Somebody else is doing it. He's still working on it. Well, I'm going to go with it. All right. Anybody else confirm this besides him?
That's what I got as well.
Okay. That would be in amps, right? Now, how do you get it back to the time domain? Don't answer, just think about it. This is a good question. I was surprised how many people don't know how. Here's where phasors become interesting. Anytime you have a time domain or a frequency domain quantity and you want to bring it back in the time domain, the general rule of thumb is this. We're going to talk about I here. I of t would be equal to the real part. And now you have to multiply by e to the j omega t. That omega was 30, but I'm just going to leave it like that. And you multiply by this, which is really 0.0479. And this has an angle. It would be e to the minus j, and it really should be in radians, but we're going to leave it in degrees for now and identify it as degrees. I'm going to call it 7 degrees. Do y'all follow me on that? That's how you get it back to the time domain. In general, phasor relationships from frequency to time are dependent on this. In general, if you want anything in the time domain, say v of t, you multiply the actual phasor term by e to the j omega t, and then you take the v phasor term, put it in here, and you'll get your time domain quantity. Now, something I have to do because I know people don't used to this. How many know what Euler's laws are, or Euler's identities? Anybody? Couple of you? They're very important. Electrical engineering, you're going to live on these things from here on out. So the first one is really e to the j theta is equal to cosine of theta plus j sine theta. How many remember seeing that, or some form of it? Okay? You all should have. The other one, there's two other ones, and you can get them from that. This cosine of theta is equal to e to the j theta plus e to the minus j theta over 2. That's a cosine identity. These things will save your life, believe me. And another one is sine of theta is equal to e to the j theta minus e to the minus j theta over 2j. These are the three commonly found forms of Euler's identity. Have you seen these? If you have, or at least remember them now, raise your hand. If you haven't seen them, it's troubling because you should be, especially with circuits. Circuits use this all the time, especially this one. All right. So when I take a look at this right here, I'm going to erase this. I'm going to use this one right here. When I take a look at this, that's a strict real number. Do you agree? That can come out in front. So now I have I of t equals 0.0479. And then it's the real part. If you don't understand what I'm doing, be attentive to this. Make sure you figure it out. Now I'm going to put e to the j, and I'll combine the exponentials, quantity omega t minus 16.7 degrees. Now, if I take a look at that, use Euler's identity here. You see how this can be broken up as a cosine of omega t minus 16.7 degrees plus j times the sine of omega t? Look at the first identity. Do you all see that, class? How many can see that? Are you good with that? Can you guys see it or not? Can you all see it? All right, if you can see it, I can move on. If you see that, the real part of that is just the real value, the cosine. The j means the sine part gets flushed. So that means you get this, 0.0479. It would be cosine of omega t, I'm going to leave it as omega t, minus 16.7 degrees. Now, I know in Dr. Irwin's book, he a lot of times leaves the angle in degrees, but you see, this is in radians. That's degrees. So generally speaking, when you're doing these problems, take this and turn it into radians if you need an actual calculation. Do y'all follow me if you're gonna put an omega t down there? Be aware of that. Anyway, that would be how you get the current using a phasor form. I'm reminding you of this because we're gonna use phasors a lot in this course, but I've gotta make sure you see that. You with me on this, class? All right. One other thing in chapter 1 before I move on. And if it gets close to the end of this class and I'm going on and on, just let me know. This is all in chapter 1, and it's sort of what I've done is well, in my opinion, it's the summary of all they're saying in there. I'll get to some of the other stuff as we need. Also, Dr. Whitmer's book, and I guess in this, in electrical and computer engineering in general, we're going to use MATLAB a lot, or Octave. How many are familiar with MATLAB or Octave? All right, Octave is free. That's why I like it. It's free. It does basically everything MATLAB does. Generally speaking, there's a seamless transition. MATLAB's a little faster, it's got nicer graphics, but they do the same thing. So I'll be giving you some work in MATLAB, maybe an extra credit or assignment or something like that, but MATLAB's something I recommend you get familiar with, and I will give you problems you can solve in MATLAB. The thing is, you're not gonna have MATLAB available for your quizzes and tests. So, in a sense, it doesn't make a lot of sense to spend too much time on that until you need to, but it's very valuable. I myself, and I might as well tell you this, I've done this stuff for a long time. I've been around a lot of smart people, really smart. I've learned that I use MathCAD. Does anybody know what MathCAD is? You do? Well, you're lucky. MathCAD is what you see is what you get. It's basically, you just pull things out, you want an integral sign, anything like that, and it will give you real-time data for anything. You can change one thing, it changes everywhere. It doesn't have to be recompiled and rerun. I'll send you a link to MathCAD, and we got a free, I think we have a whole version on the engineering website, or on the, I think it's College of Engineering website. It is phenomenal. I can only tell you that you'll see me use this stuff, and I can go through the homework problem, 20 homework problems in a second, it seems like. And I'll have all the constants, C, epsilon, mu, stored and stuff like this, and I can, most of the stuff, most of these problems, I can do a problem a minute, no problem with MathCAD. MATLAB, maybe 5 minutes. And if you're gonna do it on a calculator, it depends on the calculator, because some of them, they can really fly, I'll tell you that, but some, not so much. Anyway, now, next, now we're into chapter 2. So this is where it gets going. The way we're gonna do this course, Whitmer's book's organized this way. The first thing I talk about, or we'll be talking about, is transmission line theory, but it'll view a transmission line as simply a bunch of lumped elements, inductors, capacitors, and resistors, which you're familiar with because you just got out of circuits, most of you have. By the way, how many have had Dr. Irwin for circuits? Well, you have the best you can get. He's been around a long time, he's written a lot of books, I've taught courses with him, but he is the premier circuits instructor anywhere. Okay, now, when we talk about transmission lines, what do we mean? Well, you know what an extension cord is, right? One of the things an extension cord is, it has something that is invariant in cross-section. Two conductors that are insulated, separated by a constant distance, and the cross-section of that never changes. Do y'all follow me on that? That's considered a transmission line. It's just something that electrically holds a signal between 2 points, but our definition stipulates it cannot change in its cross-sectional parameters. Now, when you look at a transmission line, you basically have 2 wires, like such. They're separated at a given distance, but that's not important. You have some current flowing down here, but you're also going to have some leakage current that actually, very small amount, that actually flows down this way. Y'all follow me? Now that's a transmission line in a nutshell. So when we look at a transmission line, what we do is we're going to model this with lumped elements. Well, anytime you have current flowing in wire, you generate a magnetic field. Anytime you generate a magnetic field, you cause magnetic energy to be present, and inductance is now part of this field. So what we do is when we start off, if this is our actual lumped element version of a transmission line, we start by putting an inductor here. But they call it L prime because it's going to be inductance per meter. You'll see the way this goes in a second. After that, anytime you have a wire, unless it's a superconductor, it has resistance. Small as it might be, it'll have resistance. And it may be negligible. So here, we call that R prime. That would be resistance in ohms per meter. Y'all follow me? Now, I told you that there's current that bleeds off from the upper to the lower conductor, a very small amount, but nonetheless something that does happen. And the way we model that is first by a capacitor. And remember, with a capacitor, I do this because sometimes people don't remember these things. If this is a capacitor and it has a voltage V of T across it, the current I of T is equal to C dV dt. Y'all remember that? That's a current voltage relationship. Anyway, I've got a capacitor there. And then I have something, and this is something you don't use, it's called a conductance. But really, it's 1 over the resistance, but it's not the resistance in the copper, it's the resistance between the insulators per meter. Y'all follow me? It's called conductance. It's 1 over ohm meter, or really 1 over ohm meters or Siemens per meter. Anyway, that's conductance. I'm gonna leave it as just G prime. And all this is gonna be over a distance of delta Z. You can see where I'm going with this. We're gonna assume, remember, we're showing an incremental model based on lumped elements per meter, but now we get a differential length. So we multiply each of those values by delta Z if we wanted actual values. Y'all follow me? Now, there's also going to be a differential voltage drop here from here to here, a delta V. There's going to be a certain voltage drop. If you've got current flowing through a resistor and an inductor, there's some voltage drop, small as it might be. Y'all agree with that? Now we also have current flowing. And the current flowing through the capacitor right here, and this would be I'll call it these two a delta I, it's the current bleeding off. It will be equal to, if you look here, well, let me do it this way. We'll do this in the frequency domain to make things easy. So I'm going to make this have an impedance of J omega L prime, and I could say that I, therefore, I through the capacitor is going to be equal to J omega C times V. Do y'all follow me what I'm doing here? Because the DDT becomes J omega. Do y'all remember that from circuits, guys? How many do? Okay, do you? Okay, back there, guys, do you see it? All right, I gotta make sure, can you all see it from back there? Got better eyes than I do. I can barely see you. All right, so that means the current flowing here would be simply J omega C prime times V, and of course it's times delta Z, but I'm just showing you this. And the V is going to be this voltage right here, because the difference between here and here is trivial, so we just use that voltage. Then we say the current flowing here, right, it's really what? It's V over R, but since G is 1 over R, this is simply V prime times G here, or V, excuse me, times G, V prime, doesn't matter, G prime. And we've got a current flowing here, I, and now what we're going to do, remember this is going to be a delta I flowing here that's bleeding off. There's a delta V change flowing, or that occurs here. Now I'm going to write differential equations. You can read this in your book, but you understand at least the reasoning behind this. You start with a very small chunk of line. You show the differential values of the resistance, capacitance, inductance, and conductance. Then you go ahead and start writing differential equations and solve them. And that's just the way it happens in all, basically, in physics in general, unless you get at the quantum level. So here, we're going to have dV, dZ. This is the change in voltage from here to here, so we get down the transmission line. It's a drop, so there's a minus here. And that's going to be R, right, plus J omega L, and it's going to be times I, the current flowing. So that's the voltage drop that just occurs over here. Do y'all follow me? Now, it's got a minus there. When we look at the current that's actually bleeding off, the DI, DZ, that's going to have a minus sign too. And it's going to be J omega C, or really, I can put G, and these are all prime, plus J omega C prime times V. Take a look at that and just convince yourself what I'm doing is kosher. There's nothing funny about it, right? I'm just trying to take what I drew up there and mathematically express it. Now where I'm going with this is one equation with one unknown. Keep reminding yourself of that. All throughout this course and most of the upper level courses that you get into, and in physics for sure, you always want to get one equation with one unknown and find the solution. We want to find the general solution. Then we get the exact solution by applying boundary conditions. Y'all follow me? In the back there? All right. Now, for this one, we've got V and I as variables. We're assuming the cross-section doesn't change, so that means R, L, G, and C will be the same. We're also assuming it's got a sinusoidal excitation. It means it's being driven at a cosine waveform with a constant frequency. Do y'all follow me? Or a sine. But there's nothing that's not going to change. So anybody got any ideas how to do it? I know you know how. Well, what we're going to do is take another derivative with respect to z on here. So when we do, we get this. We get the second derivative of v with respect to z squared is equal to still the minus r plus j omega l. I'm going to drop the primes, it's assumed. And then I get di dz. Y'all follow me? Just took a derivative. Remember, L doesn't change with spatial distance. That's the reason you can do this. We don't assume any change with distance or with cross-sectional. The cross-section is constant. So now, what do you think I'm going to do? Remember, I want one unknown. I want either V or I. Look at the equation below that one. You see how you have di dz there? You're just going to take this and stick it over there. And then I come down here, and now I have the second derivative of v with respect to z squared is equal to minus, and here it's going to be r plus j omega l, and the I dz has got a minus there too, so it's plus, and it's g prime plus j omega c. I forget the primes. And that's going to be times v. Now I have one equation with one unknown. I'm going to come over here and continue. So, from here, now, and this is in engineering in general, anytime you got a bunch of constants that are going to keep on appearing, you try to just condense them all down to one constant. And we do that next. So we're going to say lambda or gamma squared is actually going to be equal to r plus j omega l times g plus j omega c. All right? Now that by itself doesn't mean anything, but the next step does mean something. Here, this gamma is actually alpha plus j beta. Now alpha will be an attenuation coefficient or attenuation constant. Beta will be the wave number. You'll see this shortly. So when I look at this, this right there is called a propagation constant. Okay? Alpha is the attenuation, and it's in Napiers per meter. Beta is the wave number, and it's in radians per meter. Okay, I'm just putting it down here. You get so used to this, it'll be like me writing, you know, R means ohms, R means ohms. You guys know that by now. You don't need to be told over and over. All right, but it will be. I'm just putting them down for your benefit. So when I look at this equation over here, now I really have the second derivative of v with respect to z squared, right there, is going to be equal to gamma squared, right, times v. Or I can say second derivative of v with respect to z squared minus gamma squared v equals 0. Y'all agree with that? Now that gamma is a constant. It's complex, but it's a constant. Anybody know How many have seen this before, something like it, very similar to it? If you had differential equations in physics, you saw this a lot. That's the wave equation. It's a fundamental form of a wave equation. And the reason is there's a second order derivative spatially. Now remember, I took time out of this picture, but if we had it in the time domain, there would be a second order derivative in time. And it is a form of the wave equation. How would you get a solution to that? Say it's at a job interview. Better yet, say it's for $500. Maybe that's not enough, $5,000. How would you get a solution? I'd look it up on Google, right? 90% of the stuff that I don't know, I look it up on Google or Yahoo or whatever. But anybody know how to do this? How many had differential equations? You do? Good. You had diffie-q, right? You could use Laplace transform in a heartbeat and do that, right? Do you remember Laplace transforms? You could actually use an integrating factor if you remember that from classical differential equation theory. Whitmer's book does this. I'm not going to bother going through all this with you. I'll just tell you the general solution to this is V of z, and please write this form down at least. V of z, and this is in the phasor domain. We'll have some V0 plus that I'll explain, and it will be times e to the minus gamma z plus V0 minus times e to the plus gamma z. Now, gamma z. I'm going to tell you something. After you write that down, put an arrow here and say this is going in the positive z direction. I'll tell you why in a second. And this portion is going in the negative z direction. Okay? I'm going to erase that and keep going. Okay, so this just talks about two waveforms in the phasor domain. I've already told you that's going to plus z, that's in the minus. Let's take a look at it in the time domain. Remember what I told you, if I want the time domain form of v, now v of z comma t, I would have to take the real part, right, of e to the j omega t times those two quantities. Times V0 plus e to the minus, and here I'll break out gamma as alpha plus j beta. So it'd be minus alpha z times e to the minus j beta z plus V0 minus, and here it'd be e to the plus gamma z, e to the plus j beta z. And this is bringing it to the time domain. Y'all follow me? Now, I don't know if you can see it back there. But you see how I have e to the j omega t here, right? When that's multiplied by e to the minus j beta z, I get e to the j omega t minus beta z as one exponential, right? The real part of that is what? Just the cosine. Do y'all remember that, class? So here, I can say vz of t is equal to, the real part of that is just going to be V0 plus, right here. And it's going to be it's going to actually have the exponential decay. It'll be e to the minus alpha z times cosine of omega t minus beta z. Then it's going to be plus V0 minus cosine of omega t plus beta z. And this one will have an e to the, redo that a little. This will be V0 minus e to the plus alpha z. And this is a waveform moving in the plus z direction. This is a waveform moving in the minus z direction. Now, if you actually plot those out, for each time, plot either one of them. You can plot this one for each time, and just plot it versus z. Pick a value for alpha and beta, it doesn't matter. You'll see a waveform that looks like, here's what you really see. If you look at just the right going form, just this form, and you plot versus versus z at different times, at the first instance in time, it's going to look like this. There'll be some attenuation. In the next instance in time, it's going to look like this. The next instance, it'll look like this, basically. And what you're gonna see is this tip here moving in that direction, just like a wave. As you increment time, let time get larger and larger. Y'all follow me on that? That's basic wave motion, but it's damped because it has e to the minus alpha z. If you would plot this term, it would do the same thing, only in this direction, if you start at the origin. Do y'all follow me? Now, it's real important to keep that in your mind. So now, we're gonna talk about some other features of this type of behavior. We just got to the lumped element. And Wentworth's book will talk about how you get the value of capacitance and all that, but that's a little further down the line. We do that in the next chapter. So now we gotta talk about other things related to this, like wavelength, and like the characteristic impedance. So leave that up there. And here, all right, I've already talked about wavelength, right? What I'm gonna do is just focus on the right traveling form of the wave right here. And we're gonna talk about wavelength and about phase velocity. But I'm gonna get rid of alpha. So I'm gonna make alpha 0. And here we're just using the plus z form. So now I can say my v of zt is equal to some v0 plus cosine of omega t minus beta z. Y'all follow me? We've already figured out what the wavelength was earlier, right? That was 2 pi over beta. We did that earlier. Y'all remember that? All right, now we're gonna get the phase velocity. So what does phase velocity mean? You've had it in physics, but you probably never really thought deeply about it. If you take a look at a wave in the ocean, or a wave anywhere, if it's propagating in this direction, there's a crest, right? That crest has a given phase. At the origin, it equals 0, it would be 0 degrees, right? So if we stepped on that, and we wanted to just track this thing, as time goes by, it would do this, and there'd be a difference in where the position of that constant phase portion was. Do y'all follow me? The rate that it moves, that phase moves, is called the phase velocity. So how do you get the phase velocity? Well, you come here, and you say omega t minus beta z is a constant, some c. That's a constant phase. You want to see how fast that constant phase portion moves. You with me, everyone? So what do? Well, you're going to take a derivative with respect to time. And when we take a derivative with respect to time of everything, we get omega, because derivative of t with respect to t is 1, right? Minus beta times dz dt is equal to 0, or we get really what? dz dt is going to be equal to omega over beta. And that right there is the phase velocity. That's the definition, but that's how you get it. It's omega over beta, and it assumes there's cosinusoidal or sinusoidal variation. You can't have true phase velocity for a square wave. You might say each component of that square wave have a slightly different velocity in general. So I'm just going to tell you, this is how you get it, fundamentally assuming it's a cosine or sine variation. You with me? Now, how many remember that though, from physics? Phase velocity used to be a big deal. They always test you on it. Phase velocity, what's the other type of velocity? Group velocity, or velocity of energy, right? Phase in itself doesn't mean a whole lot in some cases. I mean, if you look at an ocean wave hitting the shoreline, if you just took a look at how fast the crest of that wave moved down the shoreline, that would be considered a phase velocity. But the actual velocity of energy in a wave has to do with the direction that the crests are actually moving, not the intersection with the beach. All right? I'm just trying to give you a little perspective. So energy velocity and group velocity are not the same as phase in general. They are when waves are propagating in an unbounded medium. And I'll spend more time on that later. So now, after phase velocity, I'm over time. Am I over on your watches too?
Yeah, 12:49.
I got a minute. So I'm going to cover impedance, characteristic impedance, and a few other things. I'm going to ask you to do some reading on your own. So before Friday, we will not have a quiz this Friday. All right, but I expect you to be here. before Friday, I'll give you some homework. Please get that book. Can you do that for me? Get a copy of the book somewhere, and on Friday, we'll pick it up from there. Does anybody have any questions? I mean, you're dismissed, but if you have questions, come see me, and I appreciate you recording that. Could you get together with him? Do you have time right now to come see me upstairs or not?
Yes, sir.
You do? Okay, hang on. Any questions at all? Good. Just take a picture. Come on out.